Alrighty guys, so in today's lecture we're going to be doing a little bit more practice with dimensional analysis. We are going to be adding one thing to it at the end of the lecture, but let's start off with one example problem. So in this problem it is asking us to convert 9,000 feet into kilometers using dimensional analysis. Now we talked about this last time, but the first thing you want to do is you want to write down your givens. So what are you starting off with? And what do you want to end up with? That way we can find a path to figure out which equations here that we want to use. So our given is pretty easy. It's the number and the units that we start off with, and that's going to be 9,000 feet. So our given is 9,000 feet. And what do we want to turn that into? We want to turn that into kilometers, km. So what we want to end up with is kilometers. Now the first thing we want to do is we want to look for an equation here that contains our starting unit. Our starting unit is feet. So if you take a look at this chart, our conversion chart, we're going to look for feet. It looks like the only feet that we have is 1 foot equals 12 inches. So that means we're going to be starting with this equation right here, okay? Because we don't have one that goes directly from feet to kilometers. What that means is we need to find a path to get from feet to kilometers using these equations. So we're going to go from feet to inches. So I'm going to start off with 1 foot equals 12 inches. So I'm going to write that down here. 1 foot equals 12 inches. So what we're going to be doing is we're going to be going from feet to inches. Okay, but we need to find a path that gets us to kilometers. So if we kind of go down this line, let's just kind of go down this column right here. You're going to notice that inches is equal to centimeters. So we can go from inches to centimeters using this 1 second. And then we can go from centimeters to meters, right? That'll be the third one. So we can go from centimeters to meters. And then lastly, we can go from meters to kilometers. So we can get from feet to kilometers by using these equations. We can go from feet to inches. We can, by using equation 1, we can go from inches to centimeters by using equation 2. We can go from centimeters to meters to using equation 3, and then we can go from meters to kilometers using equation 4. So we're going to be using a total of 4 different fractions here in order to get us from feet to kilometers. Okay. Alright, so just to let you guys know, whenever I ask you to use dimensional analysis, that means you must show all your fractions, okay, in order to get credit. Okay, if you just give me the final answer, it'll be incorrect. You have to give me all the fractions, because the point of this is for you guys to know how to do dimensional analysis. So let's go through it. So we're going to write our starting number. Our starting number is 9,000 feet. And we're going to set up a fraction. Now we know that when we want to get rid of something, we're going to put it on the bottom of the fraction. We're going to put feet on the bottom so we can get rid of feet. Now we're going to use this equation right here. The number next to feet is 1, so we're going to put 1. And whatever feet 1 foot is equal to is what we put on the top. So it's equal to 12 inches. So we're going to put 12 inches on top. And that lets us cross out the feet because top and bottom cancels out. Okay, next we're going to use equation number 2 to set up another fraction. We're going to use this one right here. Okay, we have inches on the top now, and we want to get rid of inches, so we're going to put 1 inch on the bottom. And that way the inches can cancel out. Now what is 1 inch equal to? It's equal to 2.54 centimeters, so I'm going to put 2.54 centimeters on the top, and the inches canceled out. Alright, we're still not at kilometers yet, so we're going to set up another fraction. Centimeters on the top, that means we want centimeters on the bottom. So we're going to use this equation right here, centimeters. It looks like we have 100 centimeters, so we're going to put 100 on the bottom. And then on the top, that whatever it's equal to, which is 1 meter. Okay, and then the centimeters can cancel out. Okay, we're almost there. We're at meters now. Now what we're going to do is we're going to use this fourth equation, and we want to put meters on the bottom, so we're going to put 1,000 meters on the bottom, and then whatever it's equal to goes on top, so we're going to put 1 kilometer on the top, and then the meters can cancel out. So there you go. We got rid of all of our units, and now we have kilometers. So if you need to take a second to look at all these equations and see how we got to this point, you can do so. Okay, but we're going to move on and we're going to solve it out. So let me get rid of these arrows just so it's easier to see. Okay. Alright, so what you want to do is you want to make sure that you can, or whenever you're solving this out, you multiply what's on the top and you divide what's on the bottom. So our starting number is 9,000. Now, we need to multiply all the numbers that are on top of the fractions and divide by what's on the bottom. So if we take a look at this first fraction right here, 12 over 1, we have 12 on top, so we're going to multiply 9,000 by 12. That's going to give us 108,000. Now there's a 1 on the bottom and we need to divide by 1, but we can skip the 1s when we're multiplying and dividing, because if you multiply or divide by 1, the number doesn't change. So we'll skip the 1. Next we'll go to the second fraction, 2.54 over 1. 2.54 is on the top, so we're going to multiply this by 2.54 to get 274,320. Okay, we'll move on to the third one, 1 over 100. So we can skip the multiplication this time because it's multiplying by 1. But we're going to have to divide that by 100. And that's going to give us 2743.2. And then we're at our last fraction now, 1 kilometer over 1,000 meters. Or sorry, 1 kilometer over 1,000. So we're going to divide by 1,000. And there you go. We've multiplied and divided for every single number. And so our final answer is going to be 2.743, and you just need to give me 3 numbers after the decimal, and don't forget your units, which are kilometers. And there you go. That's going to be your final answer. And again, you need to get, in order to get credit for your problem, you need to give me everything that's in this box. You have to give me all of the fractions that you use for dimensional analysis, and you need to give me the final answer. Alright, so we're going to move on now to the thing that we're going to be adding on for today's assignment. What we're going to be doing is we're going to be writing our own equations now. So up until this point, I've given you a bunch of these equations, but sometimes you're going to have to write your own equations where two things are equal to each other. So let's do an example of that right here. So it says that we have a 10-pound bag of rice costs $3.99. So automatically you know that 10 pounds is equal to $3.99. So we can use these numbers to do 10 pounds equals to $3.99. Now remember, when something says, if something is equivalent to, has an equal sign, if it has the word per, if you see anything that indicates that something is equal or the same as another thing, that's when you can write an equation. So 10 pounds equals $3.99. And then it's asking us to find the price of 5.6 pounds of rice using dimensional analysis. So if you take a look at the number 5.6, it's not equal to anything. Instead, this is our given. This is what we're starting off with, because they're telling us to go from pounds to price. This is our end point. And we know that another way of talking about price is dollars. So that means in this problem, our given is going to be 5.6 pounds. And then what we want to end up with, what we're looking for, is going to be in dollars. So what that means is we are going to write it, we're going to do dimensional analysis. So we're going to start off with our starting number, 5.6 pounds. We're going to set up a fraction. We want to get rid of pounds, so I'm going to put pounds on the bottom. And we're looking for dollars. So you can use this chart right here, or you can use the equation or a combination. So we're trying to go from pounds to dollars. Do we have an equation where pounds is equal to dollars? Okay, yeah, we do. It's the one that we wrote using the information in the problem. It says 10 pounds is equal to $3.99. So that means we can use this equation right here and turn that into a fraction. So we're going to put 10 on the bottom because it's 10 pounds is equal to, so if you have something that's equal to another thing, you could put them on the same fraction, is equal to $3.99. Okay, the pounds can cancel each other out, and then you can just solve it out because you only have dollars left, and that's what we were looking for. Okay, so let's do the math now. You just multiply the tops, divide by the bottom. So we start with 5.6, and you multiply by the top, which is 3.99, and then you divide by what's on the bottom, which is 10. Okay, and there you go. You have your answer. Since our unit is dollars, we're going to put dollars in the front. $2.23. And again, in order to get full credit for this problem, you have to give me this whole thing. You have to give me the fraction and the final answer, which is $2.23. So even though this problem might seem a little bit more difficult because you had to write your own equation, it's not too bad. All you need to do is make sure you look for two things that are equal to each other, and that's going to let you create your equation. Alright, so for this next one, if you feel pretty confident trying that on your own, feel free to pause the video and solve this out. But if not, that's okay. I'm going to go through it step by step. So it tells you that a green sea turtle can weigh 25 stones. Okay, a stone is an old unit of measurement that is equal to 0.007 tons. Now, if we stop right there, it says that a stone is equal, you see that word equal, right, is equal to 0.007 tons. So that should automatically let you know, hey, this is probably going to be an equation. So it tells you here a stone. The word is equal to what number? 1. Right? If you have a cake, you have one cake. If you have a car, you have one car. So a stone, it says, is equal to 0.007 tons. Okay? And then it tells you in this problem, convert the turtle's weight into pounds using dimensional analysis. So if we look for our given is going to be the other number that we have, which is 25 stones. Okay, so we're going to write 25. Now I'm going to abbreviate it as ST. Okay, so 25 ST. Okay, what do we want to end up with? In the problem it says to convert the turtle's weight into pounds. So our ending is going to be pounds. That's what we're looking for. So we need to go from stones to pounds. So if you take a look at this, all the equations that we have on this chart or that we've written down, we want to look for the one that has stones. Now, there's no stones on this chart. I'll just let you guys know. So we're probably going to start off with this one right here. We're going to start off with 1 stone is equal to 0.007 tons. Okay, and if you notice, we can't go directly from stones to pounds, but we can go from stones to tons, and then we can turn the tons into pounds using that equation right here. Okay? Alright, so let's start our dimensional analysis. So we have 25 stones, 25 ST. We're going to set up a fraction. Whatever you want to get rid of, you put on the bottom. You want to get rid of stones, so I'm going to put stones on the bottom. Now, we're going to be using this equation right here to go from stones to tons. So the number next to stones is 1, so I'm going to write 1. And then the number that 1 stone is equal to, it's equal to 0.007 tons. Okay? And then that allows us to cancel out the stones, and now we have tons. Okay, but we're not done yet because we need to turn tons into pounds. So we're going to set up a second fraction. And for this fraction, we're going to be using the second equation. Now, I want to get rid of tons here, so I'm going to put tons on the bottom. And it tells us in this problem that 1 ton is equal to 2,000 pounds. So I'm going to put 2,000 pounds on the top over 1 ton because if they're equal, they can be on the same fraction. And then from there, the tons can cancel out. And the only thing you have left is pounds, which is good because that's what you're looking for. So now we can go into our calculator and plug and chug. We start with the number 25. We multiply what's on the top and divide by what's on the bottom. So it looks like we have 0.007 on the top. So we're going to do 25 times 0.007. That's going to give us 0.175. We can ignore the 1 on the bottom because if you divide this by 1, it'll be the same number still. And then in the second fraction, we can just multiply that by 2,000, and that'll give us 350. Okay, so we're going to write 350. And don't forget your units, which is pounds. Okay? So in order to get credit for this problem, you're going to have to include everything that's in this box. You're going to have the fractions and your final answer, which is 350 pounds. So this green sea turtle that we're talking about weighs 350 pounds, which is the same thing as 25 stones. Okay? Alright, so let's do a couple more examples. And again, at any point, if you feel pretty confident in doing this, you guys can pause the video and try it out with me. Okay, so here it says that we have a cupcake recipe for 5 eggs per 12 cupcakes. Now, if you guys remember from the previous lecture, if you ever see this word per means equals. Okay, so 5 eggs equals 12 cupcakes. And I'm going to write CC just because I don't want to write out cupcakes. Okay, so 12 CC. So if an egg has 60 grams, or if an egg has a mass of 60 grams, how many kilograms of eggs do you need for 50 cupcakes? Now this is where it might get a little bit confusing because we have a bunch of things flying around. So let's start off by writing our given, finding our given and our endpoint. I personally think finding the endpoint is a lot easier because it tells us how many. So whenever you see that term, how many, how much, find, if whatever you're looking for is the endpoint, and you're looking for kilograms. Okay, you're going to be looking for kilograms. Okay, kilograms of eggs specifically. Okay, now for our given, we can either do 60 grams or we can do 50 cupcakes. We need to figure that out. So the question to ask is, what is equal to something? Is 60 grams equal to something? Or is 50 cupcakes equal to something? Now, if we take a look at this problem, let me just erase the line so it's easier to read. Okay, so what we did was we already used this part, so we used 5 eggs, so we can ignore that. 5 eggs and 12 cupcakes for this equation right here. We can ignore the kilograms of eggs because we already wrote that down. That's our endpoint. So the real question is between 60 grams and 50 cupcakes. Now let's take a look at 60 grams. Is 60 grams equal to something? Okay, so is 60 grams is actually equal to an egg, one egg, right? One egg is equal to 60 grams because it tells us one egg has a mass of 60 grams. So that means one egg is equal to what? 60 grams. Okay, and if you take a look at 50 cupcakes is not equal to anything, right? It's just saying, you know, how many kilograms of eggs do you need for 50 cupcakes? So our given, our starting number here is going to be 50 cupcakes. And so going forward, this is why it's going to be very important that you read the directions carefully, because sometimes you're going to get all these numbers and you're going to have to write different equations and you're going to have to differentiate between them. Okay, so we have our two equations and we have what we're starting off with. So we have 50 cupcakes, so I'm going to start with 50 cupcakes. Oops. We're going to do 50 cupcakes. We're going to set up a fraction. Now I have cupcakes, I want to get rid of that, so I'm going to put cupcakes on the bottom. Okay, so the only equation that I have with cupcakes in it is this one right here. 5 eggs equals 12 cupcakes. So I'm going to use that. And so the number that we have for cupcakes is 12. Okay, and 12 cupcakes is equal to 5 eggs. Okay, so we can cancel out the cupcakes and we're good to go. Now I have eggs, but I don't want eggs, I want kilograms. So the only equation that we have for eggs is this one right here. So we're going to set up another fraction. Now I have eggs on the top, so I'm going to put eggs on the bottom, and the number next to eggs is 1, so 1 egg is equal to 60 grams. So I'm going to put 60 on the top. And then we can cancel out the eggs. Now we have grams, but is that what we're looking for? No, we're looking for kilograms. What that means is we're going to have to use another equation, but we don't have any more here. So that means we can go to this chart, and you're going to see you have kilograms and grams. So this will be the third and final fraction that we can use. So times, I'm going to set up a fraction. We have grams on the top, so we're going to put grams on the bottom, so 1,000 grams on the bottom. And then on the top, we're going to put 1 kilogram. Okay, and then the grams can cancel each other out. And then now we have what we're looking for. We have kilograms. And now we can solve out the problem. Alright, so let's plug it into our calculator. So We start with the number 50, and in the first fraction we multiply the top, which is 5, so times 5, and then we divide by the bottom, which is 12. And then we go to the second fraction, we multiply the top, which is 60, we divide by the bottom, which is 1, so we can skip that. And then the third fraction, we can ignore the top since it's 1, but we do need to divide by the bottom, which is 1,000. So for our final answer, we get 1.25, and so we get 1.25 kilograms. If you want, you can say of eggs, but 1.25 kilograms is fine. So basically, this information tells you, hey, if you want to make 50 cupcakes using this recipe, you are going to need 1.25 kilograms of eggs. Okay, so you can see that dimensional analysis has some application in real life. This is actually how I do my cooking and my planning for things. I set up fractions like this, no lie, in order to figure out how much of everything I'll need if I want to make a quantity that's not in the recipe.